Good afternoon, all of you, and welcome to this live session on this particular course, Advances in Welding and Joining Technologies. So, I have seen that you have raised few questions related to, I think, in your forum, this part for this particular course. Then few questions maybe you have asked directly to this thing, but maybe before uh, putting this thing in questions at this moment, maybe I can start discussing on the what we have some difficulties in understanding all these particular questions that you have already raised that I want to discuss first. So if you look into this for this live interaction, you pose this kind of question. First, you have asked that how do we can get the fine UX dendritic structure if temperature gradient is low. So I'll answer maybe with the one particular slide, but first look into these questions also. And so someone has asked that that very difficult to understand the graphs of a particular module. I think if we explain specifically indicate the which graph, I can explain to all of you. And someone asked that explain CCT diagram. Definitely that I'll do these things. And one question I think from some industry people that asked to fabrication of the structural material like the different kind of the steel, and basically I think you are facing some kind of the difficulties, and maybe you are getting some defects, maybe crack or solidification cracking during this welding process. But in this case particularly, I can say in very general measure all this thing why it is happening this thing. But if you want to know in details, I think it is better to communicate personally that we exactly what is your problem and what kind of things you are using, what material you are using, parent material and the filler material. Definitely that will discuss also this thing. And then so come first point is that maybe in this case that you asked that what even temperature is low, temperature gradient low, what you can influence this thing, how you can form the equiax structure. Now if we look and follow this particular slide, even it is there also. So first thing is that in a welding process, if we follow some kind of the heterogeneous nucleation process, definitely if you promote the heterogeneous nucleation process and at the same time nucleation happens several positions at a time, then that will help to form some kind of the equiax kind of the structure, because at several positions there is a formation of the nucleus at the same time. And second part, in general measure, what are the welding parameters that will affect the formation of the heterogeneous that means equiax structure. It is something like that. For example, that higher heat input and the welding speed. High heat input and the welding speed. If we follow the very high heat input and welding speed is very high, these two particular conditions actually improves or promote the equiax kind of the structure. But if you're asking why it is like that, because if you see with the increase in the heat input and the welding speed, if you see that increase in the heat input and welding speed, the temperature gradient at the end of the weld pool reduces. It is true with the increase of the heat input and as well as the welding speed, both actually favors to enhance to basically at the end of the weld pool, the temperature gradient actually reduces. And if you observe in the case of the welding problem, say it's a very high welding speed at the end of the trailing pool, that means at the end of the weld pool you can expect some zone that kind of equiax formation apart from the columnar and dendritic kind of the structure, the other zone also. So therefore in simply we can say that increase in the heat input and the welding speed both actually enhances the some kind of the promote the equiax kind of the structure. With the increase in the welding speed, the solidification rate of the weld metal also increases. So increasing the weld speed, it also enhances solidification, because if you with the increment of the welding speed, if you try to accommodate the rate of the solidification, or solidification front will try to move or try to accommodate the welding speed. So in that cases, it basically enhances this thing. So that means the G and R basically both one case is the first case is the G actually reduces this in this case, and second case is the increasing the welding speed R also increases. So therefore G by R also decreases in this particular system. And apart from this, G by R decreases and then it actually enhances the constitutional supercooling. Once the constitutional supercooling zone is very high, so that actually try to form some kind of the equivalent structure. Equivalent structure means that at the same time the several position it will try to nucleation start, and accordingly the grain growth may also happen. So therefore all these condition always favors to this thing, equivalent kind of the structure. But in practical, it is not always possible to avoid the some kind of the columnar or dendritic structure even near about this thing, the wall or maybe mold metal interface in case of casting, or in case of the welding maybe near about the solid liquid boundary. So therefore some sort of this thing columnar kind of the structure will be definitely will be getting. It's because columnar structure will always be getting the it depends on the temperature, the steepest temperature gradient in one particular direction. That steepest temperature gradient is normally exists along the radial direction, which is normal to the solid liquid interface, and that always target to the center of the oil pool. So along the from the periphery to the center of the oil pool, always we can expect some kind of the columnar or kind of the dendritic structure. So that is always there. But till if we want to promote some kind of the equivalent structure, we can simple way we can see the enhance the welding speed, very high welding speed, or welding can occur at high heat input. Both the conditions favor to form the equivalent structure. So I hope this is clear. Maybe now I'm shifting to the next question. Yeah. Someone asks this thing, that diagram, this CCT diagram or TTT diagram. So TTT diagram of the steel, we can see the carbon steel. So first we have to understand the TTT diagram in the carbon steel, that one is the transformation happens, start of this transformation. Okay, so in this case, the start of the there is a one C that there is just transformation starts one particular graph in the is a typical shape of the nose shape, and other is a transformation end. So in TTT means time temperature transformation diagram. So basically the one curve we can form one phase to another form. This transformation starts, and next curve we can follow the transformation ends. So therefore it means that if we remember that in equilibrium phase diagram, there we can form all the different phases form at the equilibrium condition, in the sense that we are allowing to form one phase to another another phase, that is for infinite time. This mathematically the long time we are allowing to follow the some kind of the cooling during the cooling process. So it means the phase transformation happens the sufficient time. So then we can get all this information from the equilibrium phase diagram. So that's why assuming that the equilibrium condition exists, based on that we can develop the phase diagram also. But in case of in practical, some finite time is required to transform from one phase to another phase. So then when you count over time, the transformation happens over a particular time. That kind of effect of the time or transformation as a function of the time can be better expressed in case of the either TTT diagram, or that means time temperature transformation diagram, or CCT diagram, continuous cooling transformation diagram. In TTT diagram, you have to understand that which is the transformation start part. That means say 0% of the particular one phase. In this case, maybe say initially the austenitic phase. Austenitic phase, the transformation in the different temperature. Of course, the austenitic phase exists at different temperature. So first line, dotted line, you can see the dotted line indicates the for austenitic start temperature. That means austenitic start. It means that 100% austenitic phase. Now over a finite time, once it reach to the next curve, then transformation from austenitic phase to some other phase. But which phases is depends on the at what temperature the transformation occurs. For example, at very high temperature, we can expect the transformation austenitic to pearlite structure. In the towards the little bit lower temperature, then the austenitic to the binite transformation. And even it is very low temperature, then the transformation when it is austenitic to the some other transformation, maybe matrixatic transformation, is as a function of the temperature also. In this cases, we are not following, we are not getting any kind of the transformation diagram. So it means that there is a zone, different zone, so zone that over which that temperature range that one phase transforms to the another phase, and following some kind of the diagram in this case, such that we'll be able to know what are the transformation happens and what particular temperature. So this is the TTT diagram. Now we come to the CCT diagram. This is the continuous cooling transformation diagram of the carbon steel. If you follow this continuous cooling transformation diagram in the carbon steel, you can see that we can follow some transformation line also. See, in this case, and we use the transformation lines means is as a function of time also. This is the one particular transformation, and within that there is a transformation from austenitic to the ferrite structure, and there is just some transformation line that austenitic to pearlite structure also. Now once we decide this transformation diagram, and then if we follow the different kind of the cooling rate, so for example this dotted line from starts from the 700 Kelvin, and this corresponds to these things, the dotted line comes downward. So this dotted line indicates one constant rate of the cooling. For example, first it indicates the 8 point, if you see the graph also, you can see that it indicates the 8.3 degree centigrade per second. That means if we follow the cooling rate 8.3 degree centigrade per second, then we can expect, or more than that, then cooling rate, it will be, if it is following the cooling rate more than 8.3 degree centigrade per second, it means it indicates the left hand side also. So then beyond that cooling rate, it will be always be getting some kind of the martensitic structure. So that information will be getting from the CCT diagram. For example, if we follow the cooling rate only 0.3 degree centigrade per second, so it's somehow less than that of the 8.3 degree centigrade, and is simply moving to right hand side. So that different cooling rate if we follow, then we'll be getting the different kind of the structure. So then this information, for example, the cooling rate between 8.3 to 0.3 degree centigrade, we can expect the structure can be mixture of the martensitic structure and bainite structure. Similarly, if you lower the cooling rate also, we can expect the structure can be martensitic, ferrite, bainite, the mixture of this thing. So then it means that continuous cooling transformation diagram, first we have to look into the solid line, the transformation diagram, and from there if we follow the different cooling rate, then we'll be able to know what are the microstructure you can expect in a funnel if you follow certain cooling rate. So that information will be getting from the continuous cooling CCT diagram. This, I think that were the main questions, and then other questions, the discussion forum, I have observed these few cases. Someone asked that conduction for the solid body, convection for the liquid or fluid, and radiation for the electromagnetic waves. It means that probably you have the difficulty to understand the what are the different mode of the heat transfer is basically active during this welding process. So first part I can say that try to understand that what way the suppose it pick up any welding problem or some other heat transfer problem also. So in this case, so weld plate is there. What we normally do, that plate is there, you just have to create the arc, or laser can be focused on the weld plate, then plate will be melting particular zone, it will create the molten pool, and then after some time you will be getting the all molten pool solidify and come back to the room temperature level. So if we consider all this complete phenomena, then in this case, within this plate, once we apply the heat flux, that means you are interacting with the boundary, through the boundary heat is applied. So once heat is applied, so temperature development will be there within this body. So then from surface to inside the body, the heat will be transferred in the mode of the conduction. So in that case, conductive mode of heat transfer will be active. So that means that is the mechanism for the heat transfer from within this medium, solid medium. Now at the same time, so once the heat will be conducted, and at the same time there may be the heat loss from the surface also, but from the surface the heat loss will be there from the surface to the surrounding medium. So maybe the surrounding medium, if we assume it is filled with air, so heat transfer from this solid medium, that means that plate, to the surrounding air, that mode of transfer will be the convection. Convection in the sense, what we can understand the convective mode of heat transfer, because in this case that surface temperature and the outside environment, the surrounding air temperature, there is some differences there. So that difference, if there is a temperature difference, then only heat transfer will occur from the plate to from the surface to the surrounding environment. But in this case, there is a need to define the heat transfer coefficient. The heat transfer coefficient depends on so many parameters, but it has to be defined so that correctly estimate what is the heat transfer from the surface to the surrounding medium. But in this case, if there is a flow of the air also, if there is a flow of the air, so heat will be carried out by this particular air. So then more heat will be the transfer from the solid component to the surrounding medium. So this type of heat transfer, we can say this convective mode of the heat transfer. Now at the same time, there is a radiative heat transfer is also there, because in radiative heat transfer what happens that it don't depends on the what are the medium in between these things. So simply there is a temperature difference between the surface temperature to the surrounding. So then in this case the temperature difference is there, so therefore the heat will be transferred in the form of a radiative heat transfer. So in this case the radiative heat transfer is basically depends on the difference between the temperature, the plate temperature and the surrounding medium. So this way we count in any kind of the welding problem that these three different type of the heat transfer is there. Yeah. So that's why I think that conductive, convective and radiative mode of the transfer, all this mode of the heat transfer is associated in any kind of the welding process. Then noted sufficient to clear exam with good marks, or else do I need to refer any other author book? Definitely, if you go through very carefully the NPTEL video lectures, there I have tried to explain this thing, but in some certain cases not in depth of analysis not there. So in that cases you can follow some kind of the references that already mentioned is there in particular area. In particular area you can follow particular references, that all the references you will be getting the in the this when you declare the this particular course, there the list of the references you can follow for a particular topic you find interest. But I hope even if you follow the lecture very carefully and at the same time try to relate the lecture with the assignment or problem also, then it will not be it should not be any problem to clear your exam. I hope so. And third question, what is the meaning of the hermetically sealed? Basically this is the hermetically sealed material is basically this is the we normally protect the material. So basic once and in case of biomedical application, in other cases also we just protect the we just pack the material such that it is completely detached from the not in very intimate contact with the surrounding medium. Maybe it's a environment, some fluid medium in case of biomedical, or some surrounding the solid medium or other kind of the medium. So it's completely sealed. So that is called the hermetically sealed. Normally we use the not hermetically sealed, so only the hermetically that term, but we can use the term the hermetically sealed component, and it is more associated with the micro welding processes. And this we have to be very careful this the sealing of this particular material when we try to use this particular material in some biomedical application. So therefore we have to choose this material also when we the sealing particular component, that biomedical application it should have biocompatibility, should maintain the biocompatibility also. So therefore looking into all this aspect, we can make some kind of the hermetically sealed materials. Then you have asked that what is the relaxation time. So I think this is related to some ultra short pulse laser welding process. So ultra short pulse, if you when try to handling the ultra short pulse and we try to understand the mechanism of the heat transfer in ultra short pulse laser, in that case that see in normal heat transfer mechanism, what we can analyze the normal heat transfer mechanism, even it's a heat conduction also. For example, there is a plate also and you apply the heat on the surface, and then immediately once you apply the heat in the surface, immediately there is a development of the temperature inside the body also. So it means that application of the flux on the surface and the development of the temperature inside the body, there is no time gap. So it may happen instantaneously. So in that cases, then there is no then we don't use this kind of terminology. So that is normally follow the Fourier heat conduction equation. But what happens in ultra short pulse laser, because ultra short pulse laser the pulse duration is of the order of femtosecond. So order of femtosecond to picosecond. So in that particular situation, that at such a small pulse duration, when the energy transfer mechanism is completely different. So in that case, once the application applied flux on the surface, then some finite time is required to transfer to the body also. So that finite time we count, and that finite time can be considered as a relaxation time. And this relaxation time maybe depends on the what are the pulse duration, what are the material, and what are the laser and interaction with the particular material. It depends all these parameters. So therefore, in that case, you should analyze this heat transfer phenomena by considering the non-Fourier heat conduction. So then, I think Somebody has tried to understand the surface active elements also, that explain the surface active element to the oil means by the flux coating and the shielding gas. But your doubt is same surface active elements affect by the adding sulfur in chemical composition of material during its casting stage. So definitely it is true, there are three different ways also. If we act the effect of the surface active element simply adding in the shielding gas, this is one way. Other way also, simply make the powder, the some halides or particular components or oxides, uh, collect this, make the powder and make the paste also kind of, and paint on the very thin layer, paint on the surface, and that can also be act as a surface active element, this particular component. But at the same time, sulfur presence in the base material already existing with the material, so that surface active may contain within the material itself also. So then in that case, this particular quantity of the sulfur may act as a surface active element. That is also possible. This is a third possibility, the already surface active elements existing with the material itself. But in this case definitely composition during this casting it can be done, but we don't know exactly the adverse effect of the presence of the surface active element. It means that definitely the presence of the surface active elements will also change the affect the material properties also. So sulfur can act in a different way also, these things. But if we, that is a different issue, and it influence the properties of particular material also. But at the same time, this presence of the sulfur can act as a surface active elements, but it is very difficult to quantify the how many quantity of the sulfur is exactly will be acting as a surface active elements, and what are the quantity will be reacting with the base material to form something else. So that is very difficult to this thing. In this case, it is very much required to do some kind of the experiments also. From the experimental investigation, we will be able to say, we make some comments on this particulars. And few cases you have asked about the solidification, but before discussing on the solidification, maybe I can have a look in your questions you have raised at this particular moment. Okay, first thing is that constitutional supercooling definitely will be using, will be explaining the when you try to explain the solidification part. I am not getting your question, that dielectric medium instead of air, what are the effect? If you clarify this, what you are exactly the question, then I will try to answer it. I am talking about Venkateswar Rao. You have asked some question, but please clearly mention the question also, then I will be able to answer it. Okay, Nis, you have asked some question, maybe electro slag welding process produce the less distortion, but in ESW that heat supply is high, then how it is possible to get? So remember, once we are talking about any welding process and we are talking about this is the less distortion, less residual stress, actually this is the very, we normally present this thing in very general sense. So in general sense means, in general this is the distortion you can expect, but definitely depends on the what are the amount of the residual stress and distortion. It completely depends on the process and normally happens during the welding process. For example, in general we can compare laser and arc welding process. We can say even heat affected zone may be very small in case of the laser welding process, then we can expect the small distortion and maybe residual stress particular to the laser welding process. But it's a very much is a relative, basically this is a relative conclusion, but it's a not exact prominent conclusion, then definitely will be getting this thing. It depends on so many parameters actually, not only particular parameter, but this take is as a very general sense that electro slag welding process produces the less distortion. So main exam the questions, I think Samir Kumar, you have asked the what are the type of the main exam questions, the nature of this thing. You just simply follow the assignment question. So similar type of the question you can expect in the exam also. Same kind of similar pattern of questions you can expect. You can expect during the NSEP exam if you follow the assignment problem. Okay. So regarding arc welding, your Venkateswara, you asked regarding arc welding process, what are the effect of the different dielectric medium instead of air? So definitely there maybe arc characteristic will completely change in presence of the in presence of the dielectric medium, because in welding what we are creating the arc, basically you are creating the arc in presence of air, but remember that at the same time it is also surrounded by the shielding gas. So there is a role of the shielding gas also for the creation of the arc as well as the stability of the arc. So stability of the arc and the it depends on the I think some role is there in case of the surrounding medium, specifically in arc welding process the shielding gas. Definitely dielectric, if you use the instead of this thing normally the air, you can use any kind of dielectric, but arc characteristic will be completely different in these cases. For example, even if you know even electrode discharge machining also, there also you can create the spark also between these two electrode also, but that is a dielectric medium maybe you use in this particular situation. So same principle what follow in the EDM process also, same thing you can expect here also in the welding process if you replace this thing. So metal removal, all these things will be different in this particular case. Or it depends on the medium also, because then in that cases it may not simply remove the material if you use some dielectric medium. So it can just hitting the medium, just hitting the material also, it may create some kind of the situation such that material removal can be done. So like electrodischarge machining also, same kind of, you just compare with the electrodischarge machining. How much question will be in the question paper, that I think the pattern is already decided, no, defined, I think. I don't remember exactly how much questions will be there, but maybe few questions, 1 marks question will be there. No, I think all questions are 2 marks questions. Maybe you can assume that total 50 questions, if it is all 2 marks, then 50 into 2, maybe 100 questions, 100 marks, like that, what I remember. Okay, how we can find out, Sachin, you asked how we can find out the residual stress in the welded joint. So in residual stress in the welded joint, you can follow some kind of the measurement technique also. For example, you have some XRD technique, X-ray diffraction technique also you can use, Newton diffraction technique you can use. You can use some kind of the mechanical method also, that simply hole drilling method also you can use. From using all these methods, you can measure the residual stress. For example, suppose you have the XRD machines also. So then what one difficulty of the XRD machine is that XRD technique for measuring the residual stress is that you can measure only on the surface residual stress. So what you can do, suppose you have the XRD system. So you measure the residual stress by XRD system on the surface. Then by EDM, that is wire electrode discharge machining, wire EDM, by using the wire EDM process, you can remove the particular layer. Then you measure the next layer, the same by using the similar procedure, you can measure the residual stress. So basically, then you have to remove different layer. If you remove the layer and measure the residual stress in the next layer. So that is very destructive technique also. But if you have the Newton diffraction, then you can measure the residual stress particular depth, even in the welded structure. Very long depth you can measure. So not necessary to remove the layer. So these are the different way. Or if you have some kind of the mechanical measurement technique you follow, for example, hole drilling method. So we just simply drill the hole in the structure. From the drill the hole, it simply sends the what is the change in the strain and what is the relaxation of the stress, and that you can measure and represents the amount of the residual stress. That is normally called the hole drilling method. It's a very mechanical method. So this way also you can measure the residual stress. I hope there is no negative marking in the questions. I hope. Structural steel problem fabrication, I already asked you, but if you tell me the in details, then I can tell you the exact problem. So in general, I can tell you that there are 3 possibilities. For example, one thing is that we don't know that what are the difference between the base material, which material you are joining, and what that means electrode material you are using. So it means that already have mentioned some kind of the standard, but I don't know the composition of the electrode material and the base material. So, so if there is a very much mismatch of the in composition for the base material and the which material you are depositing, then that metallurgical incompatibility may happen. So because of that, you are getting maybe different kind of the defects, maybe the solidification cracking normally you can expect also in this particular situation. And other cases also, maybe you can follow something like that. You do the very good surface preparation. For example, remove the layer before welding. You just remove the layer of the top layer of the particular base material. Then you try welding. Maybe you can get some solution also. Or apart from that, other thing is that you can follow some preheating method. It's a simple method. Basically, don't do the welding process exactly at the starting from the room temperature. Say some preheating, say 400, 500 degrees centigrade, raise the temperature of the material. Then you start the welding process. So in that sense, you can somehow, maybe you can avoid or maybe reduce the amount of the defect formation. But if you want to know in details how it is happening, why it is happening, then you have to investigate, in the sense that have to look more details about the materials you are using, techniques you are using in details, and maybe what are the environment condition, also which environment condition you are using, all these things. That kind of information is required to explain in detail. So in that sense, maybe you can personally communicate. You can send the email also with details. I'll send you the answer also with my understanding. So questions for every week in the final, definitely you have to you have to cover all the assignments. You have to cover all the assignments, so questions will come from all the assignments also. So don't miss any one of the assignment. So then you'll be, I think, then you'll be missing some questions in the end semester, this final exam. See, from your just electrode E, this specification, I don't understand what is the composition. That is a different. We have to follow some kind of the standard book. Then only we will to know. Base material, you have written some standard also. Then how I can understand that what are the composition of this thing from the standard? I don't remember what are the this thing. Then you have to look back the reference. This is the standard. What are the composition? So that's why I'm asking you. Please send me the details with the composition rather than the standard. All these things. Then I will give you the answer. Can you join 3D printed components with the friction welding? Definitely you can join the 3D component in the friction welding process also. But one limitation of the friction welding process is that it's a symmetric structure you can join by following the friction welding. If it's a symmetric structure you can produce, then you can join these two components by the friction welding process. But of course it depends. The welding joint not only depends only the nature of the heat source, but there is a role of the metallurgical part also. Compatibility and metallurgical issues are also there associated with welding process. So I hope 3D printing you can join the friction, two components. Okay. So I think if you have question, maybe I can shift to the other part, the solidification part. Someone asked the understanding of the solidification basics of this thing, these cases. So if you see the solidification in welding and casting, we start with this thing. We start solidification, try to understand in this way that we start with the liquid metal. So liquid metal, then there is a start of the nucleation. Nucleation happens either homogeneous and heterogeneous nucleation process. Then one nucleation happens. Then after that, it's to try to follow some kind of the growth process. So then grow, and then finally all liquid metal converted to the solidified component. But during the when it's nucleation and that grow, during the growing, when it is grow one particular, then the growth process, at that time it can follow the different solidification mode. For example, it can follow some columnar kind of structure it can form. So some kind of dendritic structure, columnar dendritic structure, or it can follow some kind of the EPS kind of the structure. Now see, this driving forces for the different nucleation process, maybe in the solidification processes, the that undercooling, homogeneous nucleation process, the undercooling is the main driving force, and heterogeneous nucleation normally happens from the pre-existing surface. But in practical, we can see the most, we can find most of the process, we can find out the heterogeneous nucleation process, because in welding process also the nucleation starts from the solid liquid interface, or nucleation starts from the some broken fragmented grains also, or partially melted grains also. So that is the normally happens in case of. So in general, the heterogeneous nucleation is maybe more associated with the any kind of the practical welding process. These are the simple calculation that we have very clearly shown that what are the energy barrier required in case of the homogeneous nucleation process and heterogeneous nucleation process, and which case it is less and which case it is more. So what in this case the solidification on heterogeneous nucleation process, if you see that one cases we explain that heterogeneous nucleation process, the driving force as a function of the homogeneous into some as a function of theta. Theta is decide the shape of the nucleus. So it's a theta is decided the if it is a homogeneous nucleation process, we assume that nucleus in the form of a sphere. We start with the assuming the spherical shape. But in case of the heterogeneous nucleation process, we assume the starting with the part of the sphere. So it starts with the hemispherical cap in that form. So in these cases, there is a parameter theta. So theta is very important. So different values of the theta, then energy barrier or maybe the delta G star can be different also. Now come to this point, the solidification of particular alloy system. So in this case, in general, the solidification in case of the alloy system, it follow the, if you see there is a solidus and liquidus temperature, and for example in an alloy system there may be some solute concentration is there. So we assume the particular solute concentration C0 in particular alloy system. Then if we follow the solidification from the C0 component, then once it starts from liquid phase to solid phase, you can see from liquid phase to solid phase, when it is some intermediate temperature between the solidus and liquidus temperature, then the solubility in case of the solid phase and solubility in the liquid phase are different in this case. So that means in this particular alloy system, the solidification of the alloy system, that exactly the solid liquid interface moves in such a way that there is a composition variation exists in front of the solidification front. So once there is a variation in the composition profile can be different. It means that sometime in the liquid phase also the solid liquid interface moves. When the solidification happens, the solid liquid interface moves in the sense that gradually it is solidifying, and then the solid liquid interface moves towards the liquid and follow the solidification process also. So in this case, just in front of the solid liquid interface, there is a the composition gradient may exist, and it normally happens in case of the binary alloy system. So once there is a variation in the composition, then the variation of the composition induces some sort of constitutional supercooling. It means that temperature can be, the solidification is normally happening lowering the liquidus solidus temperature also. So then temperature can be lower than that of the liquidus temperature, or temperature can be lower than that of the solidus temperature. So therefore, combining these two effects, the supercooling normally happens in this particular zone only because of the composition variation, so or solid concentration variation in front of the solid interface. So that is normally called the constitutional supercooling. So in these cases, if this constitutional supercooling is much more, very high amount of the constitutional supercooling exists, and then it actually try to promote some kind of the equiaxed kind of the structure. And normally constitutional supercooling is much more if particular material having there is a large difference in the solidus and liquidus temperature. In that particular situation, you can expect the large amount of the constitutional supercooling. That we can already explain this is the segregation coefficients K is defined, the CS, the concentration in the solid phase, and CL, concentration in the liquid phase, one particular temperature. And okay, next. So that we have already explained these things. Maybe I am just trying to give you some overview. Overview on this particular. Say here the basic solidification mode. It can start the planar mode. That means planar mode means the solid liquid interface looks like a plane in the form of plane. So that's planar movement. Solid liquid interface just moves. And cellular kind of the structure, it can create the solid liquid interface something cellular kind of the structure, or columnar dendritic. So it's a one this primary arm, the secondary and dendritic. So there are several directions the solidification happens in such a way that it creates this kind of the network, kind of the structure. So dendritic kind of the structure it may form. And then equiax dendritic is already it's a dendritic kind of the structure, but overall the networking looks like a kind of almost equal size of the grains in this thing. So within the grain, this kind of the structure within particular grain, this kind of the structure, that means either cellular, either polymer dendritic or either aqueous dendritic can form, but it entirely depends on the so many parameters and that solidification behavior of particular alloy system. So basically in particular alloy system, it's a very much complex situation may arise during the solidification process. So that means, so it means that if you see this figure, that its solidification starts at a several position at a time. So then it solidify, making this kind of the structure, the dendritic structure, equiax kind of the structure. Then it will try to grow and then there is a possibility of that. Suppose the primary and dendritic arm, in a case of the dendritic structure also, then that there is an entrapment of the liquid phase in between the primary, secondary, tertiary dendritic arm also. So in that part, the last stage it solidify. Then it is quite possible that when last stage it solidify, always there is some variation of the concentration gradient also, or some variation of the solute concentration may also happen in alloy, and that creates kind of the segregation also, composition. That means not non-uniform distribution of the different composition may arise during the solidification process, and all depends on the rate of the solidification. But in general, an alloy system, hardly there is a planar solidification normally you can observe, because in alloy system we can form the other form of the solidification process, because even within the particular zone the planar solidification may exist, but that may be confined into a very small, a very localized position as compared to the columnar dendritic form or aqueous dendritic form during the solidification process. So there constitutional supercooling, it occurs during the solidification due to the compositional solid changes, and definitely compositional solid changes because in front of the, if you see in this, that solute is boundary layer. If you see that this figure, that there is an interface between the solid and liquid. So it's already solidified, and then solid liquid interface moves towards the liquid. So then in this case, just in front of the solid liquid interface, there is a variation in the concentration. So that part, that zone, which acts as a boundary layer formation, what we normally form in the fluid mechanics problem, how there is a formation of the boundary layer. So in this case, we can consider that it's a solid rich boundary layer. It means that concentration of the solute are different as compared to the liquid phase. So therefore, this part creates the boundary, and if this zone is much more, then it indicates that constitutional supercooling is more. So constitutional supercooling means that temperature variation is there. If you see that this red zone in this figure also, it indicates that the temperature is lower than that of the liquidus temperature in this particular situation. So if it is much more, then much more constitutional supercooling, and if this zone is much more, this indicates the chances of the formation of the equiax kind of the, it try to promote the equiax kind of the structure during the solidification process. So then we have already explained that if you follow the lecture also, that what G and R, the solidification parameters, and how we can make some kind of the condition in terms of the G and R associated with the temperature gradient, and the DL here, the DL represents the thickness of the boundary layer at the steady state. Thickness of the boundary layer at the steady state simply represents the DL by R. So that we have already explained. We have given one particular problem also in the assignment, that how we can relate it to this thing. So here you can assume there is a boundary layer that between the solid in front of the solid liquid interface. That boundary layer we can simply estimate the thickness of the boundary layer if you know the diffusion coefficient of the particular material, and the R is the rate of the solidification. I think then accordingly we can estimate what is the value of the boundary layer thickness. And we have also explained dimensional also, what should be the dimension. So this already we have explained this. See, there is a solidification welding, the solidification mode, the planar, cellular, columnar dendritic, and the aqueous dendritic can be possible. But if you see the aqueous dendritic is possible, in this case the constitutional supercooling is much more. That zone, red zone is much more. That will create some kind of the aqueous dendritic form. So this is called the solidification mode. And effect of the cooling rate, it means that if even there is a solidification mode can be different, the planar, cellular, columnar dendritic or aqueous, but Cooling rate can be the different aspect also. If cooling rate is very high or low, based on that we can get the whether it is fine structure or coarse structure, and this thing the greater G into R. So this solidification parameters G, if you multiply the value of G into R, that actually indicates the cooling rate. So if it is very high, in this case, then you can get the fine structure. So grain structure can be smaller, or if it is cooling rate is low, you can get the bigger structure. Grain structure can be in higher in size, or coarser structure you can expect. But whether it is fine structure or coarse structure, the mode of the solidification can be different depending the value of the G by R ratio. We have already explained that grain structure that suspected to the solidification, cracking, and the mechanical properties also. So epitaxial growth is basically associated with the at the fusion boundary, and it is associated with the autogenous fusion welding process. So autogenous fusion welding process means epitaxial growth is normally promoted if you are not using any kind of the deposited material, or the we are not depositing any kind of the material during the welding process, or we are not using any kind of the electrode during the welding process. Rather, if you use the only autogenous mode, then we can expect some kind of the epitaxial growth. So this is normally happens start from the interface, solid liquid interface or fusion line. Then growth happens on particular direction. Normally in the steepest temperature gradient exists which direction? The growth normally happens in this particular direction. So this is called the grain growth initiated at the solid liquid interface and then proceeds towards the center. And you see this, it is called the epitaxial nucleation and growth. First nucleation starts, then only growth will occur. But this epitaxial growth is associated with the particular crystal structure, in particular material. So material is maybe the BCC structure or FCC structure. They normally follow, the growth normally happens in this particular direction, the 100. The 100 direction simply indicates, if you understand the unit cell of a crystal structure, then 100 means one particular axis in this particular direction. But in other cases it can be some body diagonal or maybe phase diagonal may grow depending upon the type of the material or what are the crystal structures of this particular material. But epitaxial growth for FCC and BCC is normally happens along the direction 100. So I think I have tried to in details in short the solidification part these things, but if you follow the lecture as well as I have shared the notes also. So if you follow this particular notes, I hope you will be able to understand this solidification process. I understand that apart from the this welding processes, this metallurgy part is also important to understand. At the same time, when you're dealing with some kind of the welding problem, because most of the practical welding problem may be associated with some metallurgical issue also. So some sort of understanding of the metallurgical aspect is required. That's why I put this particular module, one part. I hope it is clear to all of you. So I think that's all today. So thank you very much for your kind attention. Maybe if you have some questions, maybe you can ask, you can communicate through email, or you could place the question in discussion forum. Then we'll be able to answer to you. Thank you.